When a dense field of incoming light rays hits a flat surface, like a standard camera sensor, the distinct angles are instantly flattened. This process is called angular integration. The sensor adds up all the light hitting a single point and records an intensity value. The specific vector of every individual ray is destroyed, which removes the geometric data required for triangulation. Traditional imaging relies on workarounds to recover this data. We set up a second camera for binocular and stereo matching, or train algorithms to estimate depth based on monocular cues like shadows and object size. Physics offers a complete alternative, the Plenoptic function. Calculating absolute depth from a single vantage point requires recording the complete angular distribution of light traveling through space. Every ray's specific trajectory must be known. Achieving robust, occlusion-aware depth without multiple separate cameras requires us to abandon 2D integration and adopt a native 4D capture system. Light field imaging utilizes the two-plane parameterization, tracking rays across two distinct planes. The first plane, XY, maps spatial coordinates where light lands. The second plane, UV, maps angular coordinates, preserving the specific trajectory of every incoming ray. This resulting data structure is a four-dimensional array, mathematically expressed as L, X, Y, U, V. On a physical camera sensor, this tensor manifests as macropixel images, or MACP. A MACP aggregates spatial and angular data into a dense pixel block mosaic, capturing high volumes of angular data per spatial coordinate. This creates a highly machine-readable but visually unintuitive structure. This intact 4D tensor contains the geometric data needed to extract sub-pixel depth, but it must be mathematically sliced to be processed efficiently. Processing a raw four-dimensional array natively is too computationally expensive for dense depth mapping. We can reduce the dimensionality by taking our first tensor slice. By fixing the angular coordinates, we extract a sub-aperture image, or SAI. An SAI functions as a standard 2D perspective taken from one specific microviewpoint within the broader array. The second mathematical slice is much more powerful for depth extraction. It is called the epipolar plane image, or EPI. We create an EPI by fixing one spatial dimension and one angular dimension simultaneously. This horizontal epipolar slice collapses the visual scene into a series of horizontal or vertical linear tracks. The EPI takes physical scene depth and transforms it into a visible, geometrically strictly defined 2D pattern. Within an epipolar slice, a single 3D scene point projects onto the 2D plane. As the viewpoint shifts horizontally across the U-axis, that point traces a straight angled line. The pixel shift of that point across changing viewpoints is defined as disparity. Disparity equals the tangent of the epiline's angle. With disparity, we use standard triangulation to calculate real-world depth, factoring in focal length. This creates a direct inverse correlation. Steep geometric slopes indicate background objects, while shallow slopes represent the foreground. Historically, computer vision addressed this by deploying geometric operators, like the spinning parallelogram operator, to calculate these slopes based on local pixel variance. While the geometry of the epi is absolute, calculating these slopes with purely mathematical operators becomes fragile as the optical data degrades. Traditional geometric operators fail over textureless regions where variance drops to zero, and at occlusion boundaries where multiple epilines intersect. This has led to an algorithmic shift, replacing handcrafted geometric math with end-to-end deep convolutional neural networks. Standard CNNs use square kernels, like a 3x3 grid, which are highly inefficient for processing the strict linear directionality of epipolar tracks. The engineering solution is to design networks with asymmetric convolutions, utilizing a rectangular kernel. An n-by-1 operator extracts horizontal tracks, while a perpendicular 1-by-n operator handles vertical tracks independently. The network fuses these directional feature maps, allowing it to predict sub-pixel depth even when portions of the EPI line are occluded or missing. Deep learning preserves the underlying epipolar geometry while swapping fragile mathematical extraction for robust, learned pattern recognition. This chart shows the industry-standard HCI benchmark datasets used to validate the deep learning framework against traditional methods. By focusing on the boxes dataset, we can evaluate performance on complex occlusion boundaries, contrasting the ground truth against the traditional SPO column. Where the background and foreground objects intersect, the traditional SPO method generates significant artifacting and edge confusion. Contrast that failure with the sharp boundary fidelity achieved by deep learning frameworks like EpiNet and FastLFNet on that same scene. CNN architectures succeed here because they learn to segment and prioritize unoccluded spatial angular features dynamically. We see a similar result in high-noise environments. Comparing the SPO output for the DOTS dataset shows heavy corruption. Traditional disparity matching breaks down the undernoise, whereas deep neural networks inherently denoise the angular data through their feature aggregation layers. Treating light field depth estimation as a machine learning mapping problem provides depth map fidelity that pure geometric calculations cannot match. Even the most advanced deep learning CNNs face a hard physical limit when encountering complex, non-Lambertian surfaces in the real world. Specular reflections and transparency scatter light in complex patterns that violate standard epipolar disparity assumptions. Resolving these requires novel optical modeling and adaptive cross-operators. The secondary bottleneck is engineering. We must compress these massive four-dimensional tensor operations into multi-branch architectures for real-time, low-latency inference. We've journeyed from physical two-plane capture to mathematical epipolar slice analysis to deploying asymmetric neural networks. Mastering the 4D Plenoptic tensor enables absolute geometric accuracy from a single lens, supplying the high-fidelity spatial data required for autonomous perception.